Okay, so good day, doctor. We are from group 18, and today we are going to be presenting about our assignment 3 and assignment 4 for electrical installation design. So, my name is YEOH, and before I start my presentation, I'd like to give a brief introduction to this video. So, in this video, we're going to be talking about two elements: distribution and protection, and the cable installation system. So, why is it important to install these two systems properly? Distribution and protection is important because there will be various types of circuit breakers installed in the distribution system. These will protect the system from any current overflow or any earth leakages. The main purpose is to protect the users from any electrocution. So, another thing I'd like to talk about is the cable installation system. So the main purpose of the cable installation system is to transmit power from various distribution boards. So this section will focus on the selection of the cables and the protection of the cables. The main purpose is to create a power transmitting system that can deliver power properly and safely. Next, I'd like to talk about the power distribution of the system. So, how is load distributed? So, according to this diagram, the electrical company will provide electrical power to the main switchboard, MSB, and then the MSB will provide the power to the sub-switchboard, SSB. The SSB will then divide the power to various distribution boards, DB, and finally, it will reach to the loads. So now, I'd like to talk about the main switchboard, the MSB. The MSB is an electrical power panel that receives direct input from the electrical company. The main purpose of the MSB is to distribute the load among the building itself. So next will be the sub-switchboard, SSB. So basically the SSB is a smaller version of the MSB. The main purpose of the SSB is to distribute the load throughout various compartments of the building. And then there's the distribution board, DB. So DB receives input directly from the SSB and then distributes the power to the load. Circuit breakers are often connected to distribution boards to trip whenever there's an overcurrent or whenever there's a current leakage. So the next thing I'd like to talk about is the power factor correction board, or PFCB for short. A power factor correction board can improve the power factor of the MSB. The power factor of the MSB has to be kept above 0.85 to avoid any penalty imposed by the electrical company. So now I'm gonna briefly talk about the steps in designing the power factor correction board. So the first step is to obtain the current power factor and the desired power factor. So the next step will be obtain the value of QC and QC new using the following equations. So the third step in designing the PFCB will be obtaining the ratio for the switching sequence. The fourth step is to obtain the value of the QC step using the formula above. So after obtaining the value of QC step, a value of the capacitor that is closest to the QC step rating will be selected. So for step 6, the reactive power and for every step and the total reactive power will be calculated using the formula. And for step 7, the current is also calculated using these formulas. For QC stage, if it's less than 100 kilovar, use the formula on the left. If it's larger than 100 kilovar, use the formula on the right. So the final step is to select the MCCB rating according to the current.
Hi, my name is UTHAYAKUMAR SATYASEELAN, metric number 211090989. So today I will be presenting one of the most important part, which is the circuit breakers and its selection that we have done in the assessment 3 and also which carried forward for the assessment 4 as well. So let's begin. Okay, now let's discuss about the circuit breakers. Okay, what are circuit breaker? Circuit breakers is an electrical safety device designed to protect an electrical circuit from being damaged caused by excess current flow. and its basic function is to interrupt current flow after a fault is detected, or it will detach the metal, and it has its own mechanism. Okay, let's talk about the common types of circuit breakers that exist in the market as well as we used in this assessment. First of all, the miniature circuit breaker, which is the one of the common circuit breaker we used. Function of it is to protect against overcurrent and short circuits. Second, it's used commonly in residential and light commercial installations. Its rating current is up to 125 amperes and it may vary according to the manufacturer. Third, its operation is for to trip the current circuit when the current exceeds the rated value. Next, it has to be resetted manually. Fourth or fifth, the advantages is its compact size, easy to install, and can be replaced. Next, molded case circuit breaker, also known as the MCCB. Its function is it provides a protection against overcurrent, short circuit, and sometimes ground faults. And its usage is for industrial purpose or high powered application. Its rating current it's up to 100 amps all the way to few thousand amperes, and its operation is includes adjustable trip setting for current and time delays. It has to be manually resetted, and its advantages is offers greater flexibility with adjustable setting and higher capacity than MCB, followed by the RCCB, which is known as residual current circuit breaker. Function of it is to detect and interrupt leakage currents to prevent electrical shock. Usage of it it's commonly used in residential and commercial both settings to enhance the electrical safety, followed by the current rating. It varies, typically designed to handle small fault currents, and it may vary according to the manufacturer. Operation trips the circuit if the leakage current exceeds a preset threshold. It can be 30 amps, 60 amps, depends on the threshold for that RCCB. And it has to be manually resetted once it's tripped. Advantages are it provides essential protection against electrical shock and fire hazards due to leakage current. So this is one of the crucial components of circuit breaker. Next comes the air circuit breaker. Air circuit breaker protects electrical circuits by interrupting high fault currents, and this is usually used for industrial and large commercial installation. And for the current rating, it typically ranges from 800 amps all the way to few thousands of amperes, and it may vary according to the manufacturer. And its operation, it utilizes air as an arc extinguishing medium suitable for high voltage applications, and it has to be manually or automatically resettable. Advantages are it's handle very high fault currents and provide robust protection for large scale electrical system. And next comes the ELPR or the earth leakage protect relay. Function is to detect and interrupt the earth leakages to prevent electrical shock and fire hazard. Usage it's common in residential and commercial buildings. And operation it monitors the difference in current between live and neutral wires, trips the circuit if the leakage exceeds the pre-set threshold values of current. And the voltage ELCB detects the voltage leakage on the earth wire, while the current ELCB detects the current leakage in the between the live and the neutral wires. So this is a typical circuit breaker configuration that we used and also designed in this assessment 3. So now let's talk about the circuit breaker selection. Okay, one of the main components or the components that we considered in assessment 3 and also which carried forward for assessment 4 are mainly three, which is MCCB, molded case circuit breaker, MCB, miniature circuit breaker, and followed by the residual current circuit breaker, RCCB. So we have to refer to the standardized table of JKR specs for selection of MCB. miniature circuit breaker. So in this case, they have provided a detailed table which I have displayed in the screen according to the type of load, area, and also the specification of the wire, and followed by the suitable rating of the breaker. Okay, now let's discuss about the RCCB and also MCCB selection, which is very crucial part of assessment 3 and also later carry forward to the assessment 4. At first, we sum up the total current for each phase RYB, then calculate the total connected load, perform the increment of 30% for calculated value, then perform load balancing among three phases, not ensuring not to exceed 10% of each phase, then perform RCCB selection based on the RCCB rating table. So here is an example of it. Either it can be RCCB or MCCB. We have to look out for the manufacturer in the market, and here we can see that they have provided a rating for their specific circuit breaker. So we have to compare our value with the data sheet, and we have to choose the one a bit higher than the calculated value or the one we have obtained. So additionally, we have to refer to this RCCB rating table. Here they have provided the RCCB sensitivity for according to their installation location. For example, DB lighting or the single phase, the RCCB sensitivity should be 100 milliamps, and followed by this is the additional reference for RCCB, ELR, or OCEF selection. What is OCEF? Overcurrent and earth fault relay. How about ELR? ELR is earth leakage relay. And so in this case, right, the current is lesser than or equal to 60 amps in the MCCB. We might consider the RCCB as a choice for circuit breaker. If the current rating in the MCCB is between 220 amps to 60 amps, we might consider the ELR. Or if it's 250 amps and above, we might consider minimum of 2 OC and 1 EF. So that's for my part. Thank you.
Okay, the topic that I will explain is about the selection of the cable. Firstly, the proper type of wire selection is based on a few factors, each contributing to overall system performance and safety. Then, the voltage drop is another important factor, as too low a voltage can cause electrical equipment to malfunction and increase power consumption. For insulation is also important because it must protect it from environmental factors such as moisture, heat, and chemicals. Then for the mechanical protection of the cable is required to withstand physical stresses during installation and operation. Then we also have the regulatory compliance is important, and all the cable must comply with all local and international electrical standards and regulations to ensure safety and reliability. Now, I will explain for the main purpose to control voltage drop at 4%. So, first of all, we can maintain the optimal performance of electrical equipment. Then we can prevent unnecessary energy losses. We can reduce risk of overheating and electrical fires. Also, if we have the operation of electrical system, it will be safe. Then it can increase reliability and stability of power distribution system. Okay, the type of cable. Neutral and earth cable are essential components in electrical system that it can ensuring safety, proper operation, and compliance with electrical standards. So, the neutral cable can help balance the voltage in the system and ensure the proper operation of electrical device. Next, the earth cable provides a buffer for a current to safely dissipate into the ground. So, it can protect people and equipment from electrical fault and shock. So, the cable that have been used in our design is copper conductor, single core, 70 Celsius, thermoplastic insulated cable non-armor. So we have choose this for in our assignment. Okay, now I will explain the power factor correction. So for the power factor correction, we just refer the table for C1. So in our group, we just use the method B and method D. So we just refer from this table. Then for the cable size, we refer the table current carrying capacity. So as the for socket drawing, if the current carrying capacity is 24 ampere, so automatic the cable size is 2.5 millimeter square. Okay, that's all for the power factor correction and the cable size.
So hi, I will explain about conduit and trunking design. So what is conduit and trunking? Conduit or trunking is a protective tube or enclosed channel designed to safeguard road electrical wiring. Is commonly used in various settings to ensure safe and efficient management of electrical cable. So why it is important to have this conduit or trunking in our cable design? So it is make cable organized and protecting multiple cable in a single pass, also keeping space look neat and tidy. Besides, it also allowing to have easy access for maintaining wiring system. It also ensures complies with a safety regulation by preventing cable from being trip hazard or being exposed to the damage. So most of our design for mosque and office, we consider to use conduit and trunking, which is steel conduit / GI or trunking installation type to install the cable. Why we choose this type of installation? It is because it will shield cable from the physical damage caused by impact, absorption, and accidentally cut. Besides, it also protects cable from environmental factors such as moisture, chemical, and corrosive substance. It's also protecting cable from mechanical and environment stresses. Conduit and trunking will extend the cable lifespan by extend operational life because it gives more protection to the cable. However, for our design, for SSB3 to MSB, which is SSB from MOS to MSB, it has a distance by 100 meter away. Thus, we consider it is not suitable to use conduit or trunking installation type. So we use other installation type, which is direct in the ground, inducting ground, or underground cable. So why we consider to use this? It is because underground cable are less susceptible to the damage from weather conditions such as storm and wind. Compared to overhead line, it will reducing the risk of outages and electrical hazard. It will also provide additional protection such as from physical damage, moisture, chemical expose, and extend the lifespan of the cable. So now I will explain about the impact for society and environment. So first, we go for impact for designing distribution system, which is impact for our assignment number 3. So we go for society part first, which is a well-designed distributed system ensure the electrical circuit are managed and protected correctly, reducing the risk of electrical fire, shock, and other hazard. Like we install MCB, RCCB, and MSSB in our distribution system. Next, a well distribution system provides stable continuous power supply, which is essential for smooth operation home, business, and public service. In our case, which is office and mosque. Next part, we go for impact for environment, which is a good designing distribution system can minimize energy losses during transmission distribution, which is all the way from the supply to the load. Designing for scalability and future growth, reducing need of frequent upgrade and replacement, minimizing the resources and waste over the long term. Like in our assignment number 3, we consider to have 30% of our load to become a spare for our future improvement. Next part, we're going to talk about impact for designing wiring system and cable selection, which is impact for our assignment number 4. So we go for society part, which is Proper wiring design, high quality cable selection, minimize the risk of electrical fire, safeguard life and property. Next is reliable, efficient electrical system, improve quality of life by ensuring consistent access to the electrical load. Next, for environment impact, which is choosing the cable with appropriate conductivity, minimizing resistance, reducing energy loss during transmission, like we do in our assignment number 3 and number 4, which is we consider to choose the right cable size that fulfill the requirement of standard, like voltage drop is not exceed 4 or 3%. And lastly, choosing the high quality durable cable that lasts longer, and a good way to install cable will reduce frequency of replacement, thereby minimizing the waste.
Hello, Sejahtera, and a very good day to Dr. Zaid. My name is Desmond, and today I'll be presenting about the economic decisions made by our group when designing the distribution and protection, as well as the cable installation system. Firstly, our distribution system is centralized in the main switch room, which is located at the office building ground floor for easier monitoring and management of the entire electrical distribution network, as well as for easier maintenance and troubleshooting. This will also reduce costs when it comes to design of the distribution systems. Next, we take into account the future-proofing and scalability of our distribution system for future additional loads. Hence, an additional 30% of spare load is incorporated into our system when performing the load calculation. This design for additional capacity will help avoid costly upgrades later. For the distribution system, miniature circuit breakers or MCBs are used to protect the load from overcurrent and short circuit. This is important to ensure that the office and MOSQUE equipment and other loads are protected to avoid costly repairs and replacements if an overcurrent or short circuit were to occur. MCBs are cost-effective, ranging from approximately 10 ringgit to 400 ringgit, depending on the specifications such as ampere rating, poles, and breaking capacity. Residual current circuit breakers or RCCBs are also used in the design of our protection system. RCCBs are very reliable for protections against earth leakage currents and are essential for preventing electrical shocks and fire hazards. RCCBs are generally more expensive than MCBs due to their additional functionality or residual current detection, and their higher costs are justified by the protection against electrical shocks. The prices of RCCBs can range from 60 ringgit to 1,500 ringgit depending on the specifications such as sensitivity, ampere rating, and poles. It is essential in environments where human safety is a primary concern, such as homes, offices, and public buildings. When it comes to the main switchboard or MSB, there are primarily two options available: molded case circuit breakers (MCCB) or air circuit breakers (ACBs). MCCBs generally cost cheaper than ACBs, ranging from 400 ringgit to 5,000 ringgit, depending on the specifications. They are highly reliable for medium to low voltage applications and are suitable for protection against overload and short circuits in residential and commercial installations. They are also less suited for frequent switching operations. ACBs, on the other hand, are more expensive, typically ranging from 1,700 ringgit to 12,000 ringgit based on their specifications. However, ACBs are extremely reliable for high power applications and large-scale installations. They are designed to handle frequent switching operations and high-level faults. Their high cost is justified by their advanced protection features and better performance in harsh environments. Hence, when it comes to our design, the decision is to use MCBs for the incoming protection of the distribution system, as it is economically more cost-effective since the installation space is limited and our design does not require such advanced level of protection such as ACBs. Next, it is also important to implement power factor correction on PFC units to improve the power quality and reduce the reactive power caused by inductive loads in the system. This is to ensure that the system design will not be penalized with a power factor surcharge penalty by the utility authorities such as the National Berhad. The Malaysian standard for power factor should be maintained above 0.85 power factor. This is important to note that any lower than 0.85 power factor standard will incur a 1.5 surcharge of the current electricity bill for every 0.01 unit less than 0.85 power factor, and a 3% surcharge of the current electricity bill for every 0.01 unit less than 0.75 power factor. Hence, power factor pressure units are necessary to avoid the unnecessary waste of money on penalties and fines. The power factor pressure board of our system is placed strategically within the distribution system to optimize performance. For example, the crushing capacitor banks are designed for global compensation. Hence, the capacitor bank is connected to the bus bar of the main switchboard for the installation and remains in service during the period of normal load. The advantages of global compensation include reduced tariff penalties for excessive consumption of kVARs, reduced apparent power (kVA) demand, on which standing charges are usually based, and to relieve the supply transformer, which is then able to accept more load if necessary. The selection of power factor pressure controller must abide by JKR standards by being on the electrical material approved list (EMA). Even though the JKR standard for power factor step ratio is 6-step, our design incorporates a 12-step power factor pressure controller, as the extra 6 steps are readily available as spares for future development. The capacitor banks for power factor pressure are also selected based on EMA by JKR standards. This is to ensure that the capacitor banks can be used in the actual system and are readily to be installed in the system at any time, because the value proposed matches the value of capacitor banks which are readily available in the market. This is to prevent unnecessary extra costs for custom-made capacitor banks that match our calculated values. When it comes to designing the conductor material for our cable installation system, copper is often the preferred choice due to its excellent balance of low resistivity and reasonable cost. Aluminium is a cost-effective alternative where lower weight and costs are more critical than maximum conductivity. Gold and silver are not used due to its high cost. However, in specialized applications, gold and silver could be considered as their superior conductive properties and corrosion. Tungsten, while not commonly used for general electrical wiring, has niche applications that benefit from its unique physical properties. When choosing the material of cable sheathing for our cable installation system, the type of installation within the office building as well as within the MOSQUE building that is used is a single-core thermoplastic PVC insulated cable and are not armored, as it is more suitable to be used because of its flexibility, ease of installation, and affordability. As for the underground cable that connects the MSB that is located in the office building to the SSP3 that is located at the mosque within a 100-meter distance, the material of cable sheathing used is copper conductor multi-core XLPE thermosetting insulated cable, and it is armored as it is suitable for direct underground cable design because of the protective properties from the SWA material and high thermal stability and chemical and moisture resistance from the XLPE material, which justifies for its higher cost. When it comes to choosing the right conduit and trunking system to be used for our cable installation system, there are two options that come to mind: UPVC and GI conduits. UPVC conduits are more cost-effective and are suitable for indoor environments where lower mechanical stress and temperatures are expected. However, based on JKR standard for the electrical material approved is EMOR, only steel or galvanized iron GI conduits should be used for public government buildings. Therefore, to maintain and uphold the standards of JKR and as a professional code of conduct for engineers, the decision is to use steel GI conduit for the design of the cable installation, as it provides better safety and protection due to its superior mechanical strength and impact resistance, as well as having good corrosion and fire resistance, which justifies the higher cost. On the other hand, when designing the circuit protective conductor or earthing cable for our system, we followed Regulation 543.1.4 of the British Standard for IET wiring regulations. This is to cut costs when it comes to deciding the type of size of cross-sectional area of the protective conductor to be used for other system. For example, a 50mm square size face conductor will only require a 25mm square size protective conductor according to the regulation. However, most of the consultants would choose a 50mm square size protective conductor, even though their option is viable. A 50mm square size protective conductor would relatively be more expensive compared to a 25mm square size protective conductor. In conclusion, creating a schematic diagram for all distribution boards such as lighting, power, air conditioning distribution boards, sub-switch boards, power factor correction boards, and main switch boards require precise design process that prioritizes safety. For example, installing a breaker and its protective components, efficiency, and sustainability. In the wire system design, selecting the appropriate cable size has a considerable impact on the electrical infrastructure safety, efficiency, dependability, and cost effectiveness. Proper cable sizing guarantees that the electrical system can withstand the expected load without overheating, lowering the danger of fires and electrical failures. This is critical for keeping the insulation intact and avoiding any risks. Larger cables, while more expensive at first, can save money in the long term by lowering energy losses and maintenance expenses. An appropriate balance in cable sizing saves money while maintaining efficient operation. Adherence with regulatory standards and rules is required to pass inspections and avoid legal consequences. Properly sized cables and distribution and protective devices contribute to meeting these standards, assuring the installation safety and reliability. Thank you.